Bhavya, we are going to start soon. So this is going to be a special session where I'm going to cover a special type of uh, machine learning models called generative networks. Uh, so there are three types, three popular types. There are more actually, but three popular types. These are uh, variational autoencoders and uh, generative adversarial networks or GAN. Okay, that is the second type, and the third type is diffusion models. Okay, so these are the three types that we're going to cover today. Okay, three fundamental papers here. Okay, so we are going to learn the theory and techniques behind these models. Just a few minutes, then we will start. Okay, so we are starting now. Um, so first, what is the definition of generative models? That is what we are going to cover. Okay, so up to this point, we have covered the type of models are called. So these were called discriminative models. Uh, so what we're doing and the type of these models are suppose we are doing image classification uh, with deep networks. Okay, CNN like this, or there can be simple classification models like SVM here. Okay, okay, so Bhavna and Prabha. Okay, so we were covering today a special class of machine learning models, or deep learning models, you can say. These are called the generative models. Okay, so and there are three types that we're going to cover, basic three types. uh, Variational autoencoders, and generative adversarial networks, GAN, and diffusion models. Okay, so we're going to cover that today. And I was explaining that the type of models that we have covered till date are called discriminative models. Okay, so these are like CNN that we are using for image classification, or SVM for some other classification, or something for regression. Okay, so maybe linear regression models. Okay, okay, so what we're doing here is that uh, given a training data set. Okay, so given a training data set of pairs xi and yi. Okay, suppose n training examples we have. N training examples we have here. Okay, okay, so Manisha, I will I will be again giving the introduction that up to this point what we have covered are called the discriminative models. Okay, like we are using CNN for image classification, SVM for some simpler classification. Okay, and linear regression as well. Okay, so here what we have is that we have training data set pairs xi and yi. Suppose there are n training examples. Okay, and what we need to find here is that uh, is the uh, for some new x a, suppose xa, we need to find uh, the y value. Okay, uh, and let me see if the recording is working perfectly. Yeah, screen you can see, right? Screen is visible, and you're able to hear as well.
Sir, your voice is not clear. It's cutting in between. At the
Voice is
last of the sentence, it's cutting.
voice is not clear.
No.
uh, what can I do about this? Since you're able to understand what I've said till now,
A little bit.
little bit, right? So my sentences are not clear. uh, okay, I'll speak louder then. Okay, let's see if that works. Okay,
There's a background sound behind you.
yes, some actually functions are going on here, so that is why the background sound here. Okay,
Okay, okay.
cannot do anything about that actually. Okay, so let us continue. Okay, uh, so after training that model, what we're going to do is we're going to make predictions. So what is I'm saying is, for a given new xa value, we need to find the y value. Okay, or in a more probabilistic setting, what we need is the probability of y given xa. Okay, so y, so we have to find the distribution y for x is equals to xa. Okay, this conditional distribution is that is what we need to find in the probabilistic setting. Okay, So in probability setting, we need to find the conditional distribution of y with respect to x is equals to x say for specific value of x, and this is capital Y, okay, or random variable, okay. So means the it can be a distribution, suppose a normal distribution, okay. Okay, so this is our discriminative setting, okay. So suppose for at this value, it is a maximum value giving, okay. So this is the value of the y we're going to take, the mean value, okay. So y mean is this one. So this is our estimation of the y, okay. So okay, so this is the idea here. Now now what do I write? Okay, so continuing, now we get to generative models. So this is a special sessions that it is not going to come in the exams, okay, and this is for your own knowledge, okay, and means like these are state of the art models, okay, for image generation or video generation or something like that that you see, okay, like in modern times, as you can see this DALI model is there, okay. So so if you see DALI, okay, the image they are able to generate, okay, it is based on the principle of diffusion, okay. So we are going to go through the basics of that, okay. Advanced things you can study on yourself, okay, because you will not be able to cover that, okay. And okay, so you see with DALI we can DALI, and there is Sora as well, Sora model, okay. So here we are able to generate videos here, okay. Okay, so continuing, so okay, so continuing here, we are interested in models which give us the probability distribution x given y is equals to y, okay. So for some value of y we are trying to generate new x values, okay. So we are interested in producing this distribution for a given value of y, okay. So if we keep changing the y, suppose here what I mean to say here is that you can see this is like creating video from text, but it is quite similar actually. uh, the concept is quite similar, okay. So what I mean is that so here you give a prompt in the means like a instruction what type of video you want, okay, in the form of a prompt, okay. So what type of video that you want or image that you want is called this it is this y value, okay. So okay, what class of data do you want, okay, here uh, what class of data do you want, okay, and with that you can have the generated new training examples, okay. So this is the definition of generative models, okay. So we'll get to the papers and understand more about it, okay. uh, okay, and so okay, let's study and let's see. So the first generative models that we were able to discover is called the variational autoencoder, okay. So the paper name is autoencoding variational base because it is introducing it as a concept, rather than a uh, constructor model. Okay, that's why the name doesn't match, but the concept is same. Okay. Uh, okay, so some little bit of theory is again needed. Okay, so let me do that. Okay. Okay, the notations are not very good actually. So, so what we can do here is that first we need to understand something of the Bayes theorem here. Okay, so from Bayes theorem you can see this PB given A. Okay, this is called the likelihood. Okay, PA is called the prior, and PB is called here evidence. Okay, and to understand more, if I can find my old slides here. Mm, okay, okay. So this is called the prior, and this is the likelihood PV given A, and PB is the evidence. Okay, and so this is the first things first. Okay, and next what we cover here is wait a minute, guys. Okay, so let's come to this scenario. Okay, so we can understand better. So we are given this. First, let me download this one. of spelling mistake here. Okay, so let's cover this. Okay, so in this we are given a data set here. uh, so n data points xi are the NIID samples. Okay, and so what they're doing is that they're taking a continuous random variable z. Okay, so so it is the latent variable, as they say. Okay, so okay, so how are you generating the value of z? So this value z is generated from some prior distribution this. Okay, so we know some distribution of z, we have prior knowledge about something of this, can be anything, maybe Gaussian. Okay, 0 mean Gaussian. Okay, so this value of xi is generated from some conditional distribution p x given z. Okay, theta being the parameter. Okay, so for a given value of z we generate this distribution px given z. Okay, so this prior is this pz. Okay, and the likelihood, as you can see, is represented like this. Okay, 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 so this is the situation we have. So if a z value is there. Okay, some prior distribution we know of z. Okay, and some conditional distribution of x with respect to z, and prior likelihood, everything is there. Okay, now so these are the two problems we have here. Okay, it's very important to understand them carefully. uh, so so as you can see, uh, so what do we call this one? A marginal likelihood. Okay, this is likelihood times prior. Okay, it's called so we're marginalizing that. Okay, so we're taking integral of that to get the px theta. So when we are integrating with respect to z, for all values of z we remove the variable z. Okay, from some rule of probability. Okay, so this can be interactable. Okay, means the integration may not be solvable. Okay, and what can happen is that we cannot get the posterior density pzx. Okay, so that is one problem. Okay, so that our another algorithm is there, algorithm, expectation maximization, that cannot be used because that in that algorithm we need to find the posterior density. Okay, so this is one problem which, like, it is unsolvable problem. Okay, so so it is cannot be solved with algorithm. Okay, because the posterior is intractable in most of the situations. Okay, if you don't know about algorithm, that's okay. Okay, because we're not going to focus on that too much. Next thing is that so if there is a large data set usually to train the model, and large data set is needed as well, and so what happens is that a sampling method with Monte Carlo estimation will also be not possible to estimate the posterior density because it may be too slow, okay, because of the lot of data points. So that is the problem statement we have here, okay. We need to find the posterior here, okay. To make predictions given x, we find the z, okay. Okay, so that is the situation we have here, and so in these three directions we need to move to understand, to solve our problem, okay. So the efficient, so we need to find three problem scenarios. Means we are encountering three problem scenarios here. So we need to find efficient ml or map estimation for the parameter theta, okay. The parameters are of interest, okay. So we need to find the ml estimate, or means maximum likelihood estimate, or map estimate of the parameter theta, okay. Because what happens if we have the theta value, okay, you can uh, given a y value, you can find the some fake data, okay, or means the artificially generated data, okay, better way to say it. So this is the our direction of thought will be this, okay. So to find the value of theta, so, or an expression of theta with ml or map, so that we can get to our data generation process, okay. And next what we have here is this given a observed value x, we given also we have got the some value of theta, so we are finding the approximate inference value of z, okay. Because it is useful in representation, because we are not using x here, a lower dimensional z it is what we use here, okay, to reduce data usage, okay. And next we are trying to find the marginal likelihood of x, okay, p of x, okay, because with that we can generate data, okay. Okay, so for to solve this problem, we are introducing a new recognition model q z given x for the interactable problem p z given x. Okay, so the idea is that this may be a better method of doing it. Okay, means like it is more solvable. Okay, means it maybe like integration is possible here in this case. Okay, so okay. So little bit of understanding here very important. So the unobserved variable z have an interpretation as a latent variable or latent representation or code. Okay, so z is like a latent representation or a coded representation, a lower dimensional representation of our variable x. Okay, in this paper, we'll therefore refer to the recognition model q z given x. So we're finding z with respect to x as the encoder. Okay, so this is called encoder. So this is how encoder is defined here. This is the first paper of generative models. So we're having good definitions here. continuing. So as you can see, like first what you're doing is that we are trying to find lower dimensional z from a higher dimensional x. Okay, so z is called a latent representation or code. Okay, a coded representation. Okay, so this is called a probabilistic encoder. So because it produces a distribution. Okay, so that is it. Okay, and this is a probabilistic decoder. Okay, so that is the idea here. So first we get z with through this distribution q phi of x, then we are getting x from z with distribution p theta x given z. Okay, so this is basically the idea. Okay, now this is the main theory here actually, and we need to understand it well. Okay, so what we have covered till now. Okay, let me summarize that. Okay, so what you have is your variable x. Okay, so we're getting it to a lower dimensional variable z. Okay, through a function named q with the parameter phi. Okay, this is z given x. Okay, next what we're having is the reverse process of decodifying, you can say, or denoising. Okay, p of x given z, parameters are theta. Okay, so this is the idea, this is what we have learned. So this process is called encoding or encoder, and this process is called decoder. Okay, so that is what we have learned till date. Okay, the problem is not done yet. Okay, what we have done is formulate the problem. Okay, given a structure to the problem. Okay, the problem is finding the posterior distribution p of x. Okay, overall this. Okay, okay, so with this we can generate the values of x. Okay, so how do we achieve this? Okay, that is what we have to see. So for this we get to the concept of variational bound here. uh, so this is the likelihood, as you can see, log of probability of each of the sample. That is sum of uh, log of each probability of each example. Okay, okay, so this is our p of xi. Okay, so what they have written, so this is our posterior. Okay, marginal posterior. Okay, posterior is x given z. Okay, okay, now so now this probability p log of p theta xi can be written as a Kl divergence. Okay, plus this is called the lower bound of the uh, variational lower bound. Okay, lower bound on the means like variational whatever what it was, variational, it is called elbow expectation. Let me see here. Expectation lower bound. Okay, so it is the lower bound of the expectation here. Okay, first we need to define what is scale divergence for sure. Okay, so for that let me show you. this is the definition of scale divergence. Scale p by q is a summation over all x, okay, px into log of px by qx. Okay, so this is called the scale divergence, or it is type of statistical distance. Okay. Now what we have here is that so this is can be written like this. Okay, and there is a review paper as well, which I can show you, where the derivation is also there. I'll show you the review paper as well. So this is the thing that we need to do. Okay, so we have this joint distribution of px comma z. Okay, so we can marginalize with respect to z, okay, to get x. Okay, this is the idea I said as well. Okay, that is not possible because it is intractable. That is the problem we have. Okay, next what you're having is that you can write this as like this. Okay, from chain rule of probability. Okay, so as you can see, a little bit download as well this one. Okay, so if you try to cover this, so what's the idea? So this directly computing and maximizing the likelihood px is difficult because we need to integrate out all the latent variables z. Okay, as I said as well. Okay, so without having access to the latent encoder z given x, it is quite hard to do. However, these two equation we can derive, take a term called the evidence lower bound. So we can find the evidence lower bound, or also called the lower bound of the evidence. Okay, so we're finding the expectation with respect to a with this coding distribution, or what we call this encoding. Okay. Okay, and so 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 this mathematical expression is valid. Okay, there's derivation of this as well, but not going to show it here. Okay, okay, so this remains valid. Okay, expectation with respect to q phi of this px, okay, is always less than the log px. Okay, no, derivation is here. Okay, no problem. So so this q phi z given x is the flexible approximation of variational distribution parameter phi. So that is what we're trying to optimize, the phi value, and so it seeks to find the approximate true distribution p when it tries to go as close as possible to the approximate true posterior pz given x. Okay, Okay, so the derivation is like this. Okay, so this integration. Okay, so log of this. Okay, or you can say that log of expectation. So expectation is, is 1 by q. So they have used this approximation of using the approximate posterior, then the real posterior, because the joint distribution here. Okay, and they multiplied both up and down with the approximate posterior distribution. Okay, so this has become expectation of this. Okay, the expectation is like this, variable times the PDF. Okay, so this is the expectation we have got. Okay, okay, so this is the with Jensen's inequality we have proved this formula. Okay, just remove the log and you can have Jensen's inequality. There's some deeper understanding as well. Okay, so deeper understanding is something like this. So if you simplify this, it gets to the point like this is KL divergence plus this. Okay, so KL divergence is actually the lower bound of the this log of px. Okay, I mean this is called the this is the lower bound. Okay, because scale divergence are always greater than 0, so we remove this. Okay, and you can put this inequality. That is why it is called evidence lower bound. So it is px is evidence. Okay, as you can see, joint density divided by evidence will be here. Okay, and this is the posterior. Okay, from the Bayes theorem. Okay, so that is why it is called the evidence lower bound, because it is lower bound of the evidence. Okay, so this understanding is important. We can move further. Okay, so next you can see, so this is the proof that we have done before. So this is the KL divergence along with the evidence lower bound. Okay, so it is the KL divergence of the approximate from the true posterior. Okay, since the scale divergence is non-negative, the second term is called the variation lower bound. So it can be written like this. Okay, so we have seen that from the other paper as well, and with logarithm rule it can be written like this. Okay, this evidence lower bound can also be simplified like this, as you can see. So we want to differentiate and optimize the lower bound, this one, this with the variational parameter phi and generative parameter theta. So with theta we are trying to generate, right? So here you can see, with this theta parameter we are trying to generate x with respect to z. Okay, and the variation parameter is phi. Okay, we have not defined what is variational, but there is a lot of thing there. Okay, okay, so that is what we have done, and so the gradient of this lower bound with respect to phi can be hard to calculate. Okay, so that is why we use Monte Carlo gradient estimator. Okay, so what we are doing is, so this we need to find. Okay, and for that what we have done, it is the mean of the all the all these means what we're doing is we are sampling the values of z here. Okay, we are putting it the values here to calculate this expression, which is the uh, approximate derivative. Okay, right? But it has very high variance. Okay, so it is not possible for practical application, and also this Monte Carlo gradient estimate is quite slow. Okay, so that is how we get the our this new algorithm for generating new data points. Okay, so it is here, not very easy, complicated, I understand, but let's try to cover still. Okay, so we've chosen an approximate posterior distribution here, and with what we're doing is that we can reparameterize the random variable z using a different transformation. So we're using this transformation g of phi ex for the auxiliary noise variable eta. Okay, so this is our function of, let's say, function g with parameter phi with e and x, and this is z. Okay, so z we're reparameterizing for with this e or eta value. Okay, and e has been derived from a probability distribution pe. Okay, so we are getting e here, putting here, and we can get the z. Okay, so we have reparameterized with eta value to get this our value z, because with reparameterization the expression remains the same, and this way the calculation is easier. Okay, so we apply this technique to variation lower bound in equation 2, as you can see this one. So we need to derivate take derivative and maximize this one. Okay, so we've done that. Okay, and it comes out to be with Monte Carlo approximation like this. Okay, and with this parameterization trick. Okay, so that is what we have done, and so this critical part is the taking derivative of the lower bound, okay, of the evidence, and then update using SGD or ADAGRAD. Okay, these are optimizers. Okay, okay, so this is our understanding here. uh, so they're using many batches as well, not training at once. Okay, there is the thing, the idea we've got it right. So with this they can estimate this lower bound. Okay, and this lower bound, as you can see, is the lower bound on this one. Okay, okay, so with that we can get the parameter theta and phi, and with the parameter theta we can generate new values of x, because you can see theta is the parameter of the decoder. Okay, so we get the theta, we can generate new values of x. So we're covering. Okay, so just last part is left. Okay, this in this paper the important part is reparameterization trick. Okay, so we need to cover this, what type of reparameterization they're talking about. Okay, so there's a essential reparameter. It is quite simple actually, so let's see. So z is a continuous random variable, that is what we considered before as well. So it is derived from this just distribution. Okay, so it can be written as this deterministic variable as well. Okay, for from function g phi. Okay, so this is it, right? So this reparameterization trick we need for this distribution. Okay, so this is how we have done. So this is mapping, discriminative mapping. Okay, and deterministic mapping. Okay, and so what we have written is that this distribution with product over all this dz, okay, small dz, is equals to our parameter like this. Okay, so idea is basically like this, that this integration you have to calculate, so it can be replaced as z with e here. Okay, and then you can do the integration. Okay, so that is how we can approximate it to a this function like this, and this summation is coming from the Monte Carlo approximation. Okay, so we have taken the general case of the common case of quotient distribution, in which we are taking this distribution, z varies by this distribution, and this is the parameterization trick. Z is equals to mu plus phi sigma, and this e varies with normal distribution 0 1. Okay, so this changes to this. Okay, as you can see from here, we have just put the value of z here. Okay, and we get it. Okay, so that is the idea here. This completes the paper of variational autoencoders. Okay, used to generate images. Okay, so it wasn't actually too good. Okay, so there were development of several other generative models. Okay, we'll take a little break here. Okay, and they will get started after say 5 minutes. Okay. Okay, everyone. So continuing. Uh, so we get to GAN now. So let me download this paper. Okay, so focus on generative adversarial network.
Hello.
Yes.
Will she going to share this?
These papers. Yes. Okay. Sure.
Yeah, yeah,
You can just search it as you find. Uh,
yeah, yeah, I got it. But
okay. Got.
other your PPTs and all will be there, right?
PPT I haven't written much. Two slides maybe. Okay.
Okay. Yeah. Okay. Thank you.
Okay. Yes. So this is our problem framework. We're going to understand from the abstract here. Okay. So uh, not able to select here. Maybe yes. So here we trained two models. A generative model G that captures the data distribution. Okay. And there is uh, another discriminative model D that estimates the probability that a sample came from the training data rather than G. Okay, so very important concept to understand here. Okay, so what we are doing here is, so we're going to cover GAN now. Okay, so here we have two models inside one model. Okay, means inside this GAN model, one is a generative network. Okay, and another is a discriminative network. Okay, so both inside a single model. Okay, so this is represented by D in the paper, and here it is represented by G. Okay, so we have two models inside the same model. So this generative model network, after training we produce our variable x. Okay, so what I mean, so after training of the GAN, after training, so TR, this G produces x values. Okay, so that time we remove the discriminative network. Okay, discriminative network is only for training of the generative network here. Okay, so both are inside this generative adversarial network, and so let's understand more about it. Okay, so the training procedure of G for G is to maximize the probability of D making a mistake. Okay, so you understand this, right? That so we're trying to uh, train the model G such that there is maximize the probability of uh, D making a mistake. Or what do you mean, trying to mean that we are trying to produce a so perfect image from G that D cannot understand whether it comes from a true data distribution or came from the fake generative model G. Okay, so that is the idea. This framework corresponds to a minimax two-player game in the space of arbitrary. Okay, so this comes from the concept of game theory. So a min-max two-player game. Player are this G and D. In the space of arbitrary function G and D, a unique solution exists with G covering the training data distribution, D equal to half everywhere. Okay, so the G covers the training data distribution. Okay, means it is trained over the whole data distribution, and D produces the value
half. What this means is that probability is half. It is confused exactly in between whether the data comes from uh, this true data distribution or from the generative model G. So it can be trained with backpropagation. Okay, there is no need for Markov chains or unrolled approximate inference networks. Okay, this will be important in the case of diffusion that we see here next, but in this case it is not required. Okay. Okay, so this is the theory here. Okay, we're going to cover that. Okay, so adversarial net they have defined here. Okay, so these are both the models are deep networks here, multi-layer perceptrons as I say. Okay, so you understand the multiple layers of the neural networks, and so what we're trying to do is to learn the generator distribution PG over the X. We define a prior on the input noise variable P, Z, Z. Okay. So G is the differential function representing a multi-layer perceptron with the parameter theta. We also define a second multi-layer perceptron. This so a second multi-layer perceptron with second neural network for D, which outputs a single scalar. Okay, whether it is belongs to this class or not. Okay, so 0 or 1. So a probability it will give. Okay, okay. So that is what is written here. So we simultaneously train G to minimize this probability that it is not from the data distribution. We're trying to minimize that. So it says that we desire that it says it comes from the data distribution. So it is this min max game. Okay, so well minimize with respect to G. Okay, so we're trying to minimize the uh, so whatever that is, so with respect to data, x that is coming from the data, we are trying to find the expectation of the dx, okay, log of dx, and another this, okay, and so that is the idea here. Okay, so this expression um, we need to see. Okay, okay, so this expression is what we are saying. Okay, and so these things are there, the analysis is there. Okay, not very important here. Next go to this. Okay, so the generator G implicitly defines probability Pg as a distribution sample Gz. Okay, when Z belongs to Pz. Okay, okay, so we're generating distributions of Z. Okay, with this generator G. Okay, therefore would like the algorithm want to converge to good estimator of P data. Okay, that is important. Okay, so because this okay G will be used to generate the data samples. Okay. So what we are doing is that we are sampling many batch of noise samples Z from prior this. Okay, suppose normal distribution is sampling from that. Okay, uh, so we sample the data as well. Okay, so upon update the distributor by after that we update this using the stochastic gradient descent. Okay, this is the cost function here as you can see, and for loop ends here for many batches, and then many batch of m noise samples from noise prior this use generator by descending its stochastic gradient. Okay, so one we are maximizing here, ascending, okay, and this minimizing. Okay, so that is the difference here. So the optimal distributive value is this one. Okay, p data of x by this. Okay, and this is the training criterion. Okay, so this is the we'll find the proof of that here. Okay, so they have defined the proof here. So at optimal value they put this value. Okay, and like that. Uh, so these are some calculations are there. Okay, not very important. Okay, we'll go over that those. So this is the concept of generative models, generative adversarial network. When a where a generative network is trying to fool the discriminative network to produce better. Uh, that is the training process. Eventually, it will be better at generating new data samples. Okay. Next concept that we go to is diffusion here. So, so now we cover the most important paper here, the latest model, diffusion model here. So this was the first breakthrough paper, okay, for diffusion, okay. So in diffusion, what happens is that at the forward process, we are repeatedly uh, adding noise, okay. Am I correct here? Okay. So let's continue. So forward process here gradually adds Gaussian noise to the image sample that we have here, okay, and the backward process gradually removes the noise that we have added from the forward process. Okay, that is the idea. Okay, so this is the background we have. Very important section. We have to read this one. Okay, so this diffusion models are latent variables of the form this. Okay, so what we are doing is that this is the joint distribution from the variation you can remember. Okay, so x and z was there. So here there are several in the form of Markov chains. Okay, so this is called Markov chains here. So this from x0 we are in the forward process we are adding noise getting to xt. In the backward process we are removing noise and getting back our image during the remove. Okay, so this is the training process. We add noise and then remove to get the image. Okay, after the training you can just use a noisy image, and from removing noise from that you can generate different image samples. Okay, so so this is it. Okay, so this is called the our posterior. Okay, okay, so this is this we have to take integration of this joint distribution. So these are latent variables. The joint distribution is this is called the reverse process. Okay, this is what they have defined as the reverse process. In the reverse process we are removing the noise. Okay, so it is defined as this xt. normal distribution xt, variable is xt, and 0 and I are the okay. So that is it. Okay, and this joint distribution can be written like this because is a Markov chain, so Markovian property holds. Okay, so 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 what happens is that idea is this xt minus 1 is only dependent on xt, not on xt plus 1, xt plus 2, etc. Okay, only on xt. So with that you can have this. Okay, capital T and then the continuous product of this form. 1 minute. Okay, let's continue. So this is what we have here. Uh, so this joint distribution can be represented at the probability of the first. So this is the noisy one, extreme noise. Okay, and then the conditional distribution repeated one after another for t steps. Okay, product of these. Okay, so so they have represented this probability as a normal distribution. Okay, with xt minus 1 is the variable because it is. Okay, and the mu and sigma like this. Okay, which is from the xt and t at tth point. Okay, okay. um, so this is the one. Okay, so the approximate posterior distribution is q. Okay, q x1 to t x0. So this is a forward process. From the forward process we have, which is adding noise. Okay, okay. So these are also following Markovian property, so distributed like this. Okay, and these are the distribution means for each conditional and represented like this. Okay, okay, and so we are adding noise according to a schedule, beta. Okay, beta 1 to beta t, which is usually like 0, 0 0.1, 0.15, like that. It is increasing in step like that. Okay, so that is how we got this conditional distribution. So we are deciding how to write this one. Okay, in the code. Okay, but this has to be found out in the reverse process. Means uh, when you are removing the noise, the algorithm needs to find what this mu and sigma is going to. But in the forward process, we are defining it ourselves, the beta t values. Okay, so this is the idea, and from the VAE paper, you would remember that this expectation is less than this. Okay, so we used extra minus here. Okay, otherwise it is greater than equal to. Okay, so writing this, you can get this one. Okay, the product changes to summation in log. Okay, log is applied over it. Okay, now the forward process beta t can be learned by reparameterization or halt constant. So we can define like that. Okay, it is on our cell. Okay, and next what we have is that so they have used a different notation with alpha t to write it like this. Okay, just a transformation. Okay, nothing typical here. Okay, define the alphas like this. Okay, and so the this elbow can be this one. Okay, can be reduced to this form. Okay, derivation is here in this paper. Okay, derivation is this one. Okay, big one. so you can refer this. Okay, so this elbow can be represented like this, and and this forward process, this mu t and beta t are defined like this. Okay, the derivation of this is also there. Okay, so you can see. So with this we can find the repetitive steps under which the denoising can happen in the forward process, in the reverse process, I think. Yes, in the reverse process we are denoising. Okay, so algorithm is also defined here. Okay, so here we have to use this as the cost function here. Okay, this is our cost function with e as the parameter of the cost function, and there is this training algorithm of the model, forward process and reverse process. Okay, there. So we take gradient of this cost function, and in the so in this there we are using it for inference. Okay, take the values of alpha and then you can get the x0 values. Okay, so this is the idea here. Okay, for denoising paper. Okay, and this is another important thing which okay, with this you can directly find x0 from xt without going through iterative process, because in the iterative process you have to get xt minus 1 first, then xt minus 2, and repeatedly to x0. But with this formula you can get the x0 directly. Okay, another important thing that was. Okay, other than that nothing is there. You can implementation is important to understand this paper. Overall you got the idea, I think. So this is the latest paper on diffusion. Okay, most advanced. Okay, best generative model that we have till date. Okay, so this is the concept of diffusion. So I hope you enjoyed this special session. These are not in syllabus, this is for your knowledge. Okay, which is generative models, very important but not covered in the syllabus. Okay, so it does not come in the exams, but the concepts are quite important. Okay, uh, okay, thank you very much. Any doubt? No doubt, right? Okay, thank you. We finish up here.